Hey class, happy Monday. Thank you for tuning in, and in this video my goal is to help you with this week's material on population ecology. How do populations change in an ecosystem, specifically helping out with understanding the reading in chapter 4.1 and helping you out with the population growth worksheet. Alright, and let's start at the top with a population. Okay, so a population is the number of organisms of the same species in the same ecosystem. So I have this beautiful picture of the much loved pigeon that frequents our campus, that calls Clovis East home. So a population of pigeons, these are rock pigeons or feral pigeons, is just for one ecosystem. So just the rock pigeons at Clovis East ecosystem. That's it. I'm not going to go count the rest of pigeons in Clovis. I'm just going to focus on Clovis East pigeons. Okay? And this population of feral rock pigeon is always changing in number of individuals. There are births, there are deaths. Pigeons are going into Clovis East. They're immigrating. They're exiting Clovis East. They are emigrating. So, when we look at population changes, we focus on 4 basic mechanisms. One is birth rate. So, how many new individuals are being born? How many pigeons are being born in a month, in a year? And then death rate, the number of deaths in a given period of time. So, how many pigeons are dying in a year? Immigration. How many individuals are going into a population? They are entering a population. So how many pigeons are flying into Clovis East? And then emigration. Individuals exiting. Exit, emigration. How many pigeons? They're taking off. They're looking for a new place to call home. Okay. So if a population's increasing, so I don't know, you've been wondering about pigeons. You haven't been on campus. You're like, man, what is going on with that pigeon population at Clovis East? Are they leaving? Are they taking over, multiplying like crazy? What's going on? Well, if we want to quantify it, here we go. So the population will increase if there are more births than deaths. The number of new pigeons being born every month is greater than the number of pigeon deaths. So there are more pigeon babies being born. Okay, second thing to think about, there's more immigration than emigration. So more pigeons are flying in to Clovis East than are leaving and finding a different place to call home. So your population's going up if you're having more babies and you are welcoming more individuals into your population. Now the opposite happens when the population decreases. So there's more deaths than births, so more pigeons are dying than are being born. Okay, or more of them are leaving or emigrating than they are immigrating and coming in. So a equation to use to quantify population growth, you're going to add births and immigration up. So how many are being born, how many are immigrating, and subtract it from the total deaths and emigrations that are happening, and that will give you your population change. So let's just say, what's the pigeon population change for 1 month? Okay, we've been gone. We want to know between April and May, while everyone's been gone from Clovis East, what's been the population change of pigeons on campus? Have they taken over, or have they all died off because their food source is gone? They can't steal your lunches anymore. Well, okay, so we gotta calculate our 4 measures. Births, 30 pigeons were born. Deaths, 2 of them kicked the can and died. Immigration, 10 new pigeons from Buchanan flew in, but 40 pigeons said, this place is no good. I miss human food. I'm gonna go find a different habitat. And so you quantify these numbers, and you do some math. You're going to add up births and immigration, so 30 plus 10, and subtract it from deaths and emigration, 2 plus 40. So 40 minus 42 gives us -2. Clovis East lost 2 pigeons. in this fictional example. So the population hasn't changed much. You come back to school and you go, looks about the same. The 4 measures we used, they kind of balanced out. All right. Now, another thing you're going to see in a textbook is graphs. So how do we model population growth graphically? So let's get away from pigeons and look at something much more appetizing. Chocolate milk. You love chocolate milk. Let's imagine a scenario where you go to take out a bottle of milk from the fridge and you start sipping on it and you're like, man, this is great chocolate milk. I love it. And then your mom or dad, they yell at you and say, hey, you forgot to do your chores. Do your homework. Blah, 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 blah. You freak out. You put your milk on the counter. You go run off and you go take out the trash and you go try to do your biology homework because it's due today. And you forget about your chocolate milk. Well, bacteria naturally live in milk. Bacteria live on your lips, and so some of them get into your chocolate milk. And chocolate milk is this wonderful growth medium for bacteria. It's got sugar, it's got milk, it's got fats, it's got some vitamins. It's a great environment for growth. There are no predators in chocolate milk. And some species of bacteria can double every 20 minutes. So bacteria start growing. So that first bacteria cell in 20 minutes doubles to 2. 40 minutes go by. Boom, it's doubled. So now there are 8. Or now you have 4. Those 4 double. Boom, an hour goes by. You've added 8 more. 16. Your population starts doubling. And if we graph that, so at time 0 with 1 bacteria, 20, 40, 60 minutes go by. We're at 8. Not so bad. 8 bacteria. I'd still drink that chocolate milk. Another hour goes by. 60, 80, 100, 120. I'm up to 64. All right. That's kind of starting to get up there. I don't know. Maybe I'd still drink it. 3 hours go by. 140, 160, 180. I'm up to 528. That's a lot compared to the one I had just 3 hours ago. So in the first hour, I just grew by 8. The second hour, I went from 8 to 64. Okay, so what is that? 54? 56 increase, and then about a 500 increase in the next hour. So it's doubling every 20 minutes, but that doubling as the population gets bigger can take a population and make it grow out of hand. So this type of growth, when a population has unlimited resources, there are no limiting factors, is called exponential growth. So the population is growing at a fixed rate, and its growth increases as the population gets larger. And we'll call this a J-shaped curve. Okay, so large exponential growth. We're doubling every certain amount of time. We're going up 50% every hour. We're growing 3 times every month. And as that continues, the population gets larger and larger and grows faster and faster. So, but exponential growth, it has two phases. The first is this little lag phase. So at the beginning, you don't notice a whole lot of growth. It's doubling, but the population, it's adjusting to its environment. It's taking advantage of resources, but the population is a little too small to see big growth. So one bacteria can only do so much growth. And on a graph, it's not going to look like a really large increase. But as time goes by and your population starts growing and being able to take advantage of those resources very well, you have this exponential growth where the graph really starts to curve upward. Now, that's great. And if you kept feeding this bacteria chocolate milk, kept adding more to your bottle, you can keep getting that exponential growth. But ecosystems aren't constantly being fed resources. Okay, and like this milk bottle, at some point, the milk is going to run out. The bacteria will eat all the sugar. And so this exponential growth can't happen forever. And in ecosystems, it does not happen forever. And instead, we reach a carrying capacity. So this is some maximum population that an ecosystem can support with its given limited resources. So that chocolate milk bottle only has so much water in it, only has so much sugar and food in it, it only has so much space. At some point, those bacteria will reach a certain population that that milk bottle can support. And that can change depending on the organism. Now, if I put chocolate milk bottle, it can't support more than one human, right? So it's limited there. So different sized organisms with different strategies, with different requirements, are going to have different carrying capacities in the same ecosystem. Okay, and so more often you get something called logistic or S-shaped growth. Okay, so this is this growth pattern where you have this lag phase, it shoots up, and then it kind of flattens out as the population reaches a carrying capacity. Okay, and we will call that carrying capacity K on a graph. You'll see that often as a K. So again, lag phase, rapid population growth, and then that growth rate slows as there's more competition, resources start running out, and you have this flattening where a population kind of reaches this balance between number of organisms and what resources they can acquire in the environment. Now, organisms, they don't really know about their carrying capacity. They don't, these moose don't know that if there are 100 of them in a forest, that's all that the forest can support, okay? Bacteria in chocolate milk, they don't know, okay, after 5,000 bacterial cells, we're going to reach our carrying capacity. No, they're just trying to get as much food and make as many babies as they can. And so you can get times in a population's history where it goes way beyond a carrying capacity. It just takes off past it. We have this overshoot where exponential growth shoots past its carrying capacity. So say the population was right about here, and instead of starting to level off, since they are growing so fast, they just double and produce a ton of babies. And now all of a sudden, the ecosystem has more individuals than it can support. So a lot of those individuals die. And competition and starvation and all this stuff, predation happens, and boom, the population goes below its carrying capacity. Well, now there are more resources that the population can use. So you start having this growth again. And then it shoots back and then dies off. So oftentimes in ecosystems, you get this logistic growth with this flowing wave S pattern, where lag phase goes to exponential growth, and then as it slows, it sort of fluctuates up and down here along that carrying capacity line. All right, so I'm going to stop the video here, and then I'll make another video where we'll talk about some factors that change this graph. But overall, you will see exponential growth, J-shaped, but in real life, you'll see this S-curve with this fluctuation as organisms reach a carrying capacity, because ecosystems have a limited number of resources, but populations will overshoot that carrying capacity because they don't know that they're reaching a carrying capacity. Their goal is to acquire as many resources and to make as many babies as possible, and that can result in these fluctuations that happen along the carrying capacity of a population's growth. All right, watch this video, hope it helps, and stay tuned for some other videos that I'm going to post.